there, tech enthusiast. Imagine a tool that lets you turn those complex math equations from your textbooks into the real-world signals that you can see, hear, and analyze. Sounds exciting, right? Well, that's exactly what ETT101-40 Signals and System Add-on Board does. Designed for EMONA ETT101C experimenter, this incredible board takes the guesswork out of learning digital signal processing, circuit analysis, and signals and system. With this board, you are not just learning the theory, you are just diving into the hands-on experiment and exploring how signals and systems behave in the real world, bridging the gap between abstract concepts and practical applications. Whether you are a student or an educator or just curious about how the signals and wires and waves interact, this board is exactly the gateway to understanding the fascinating world of modern engineering. Stick around as we explore its amazing capabilities and see how it can transform the way you learn and teach signals and systems.
Here's why ETT101-40 board is so special. A clock integrated dump and hold unit, perfect for exploring signal timings and processing. A continuous time integrator, allowing you to dive into real-time signal integration tasks. An arbitrary waveform generator, which lets you create and analyze a wide variety of custom waveforms. And the heart of the board, the DSP engine, loaded with range of pre-programmed filter structures ready to tackle your signal processing needs. Best part, all of this is seamlessly controlled and programmed via USB, making it super easy to set up and integrate your.
Whether you are analyzing the signals or designing a filter or experimenting with advanced waveform, this board has covered you.
A soft front panel refers to a virtual control interface typically accessed through a computer software program that allows you to adjust parameters and control different aspects of an experiment on ETT101-40 board without physically interacting with physical knobs or buttons on a traditional front panel. Essentially, it provides a digital interface to manipulate the experiment settings on the hardware. A comprehensive lab manual covers 15 introductory level experiments designed to provide hands-on exercises covering most of the key concepts and challenges in an undergrad signals and system courses.
Next, let me show you how all these components come together to make signals and system not just easier to learn but actually fun to explore. Stay tuned. Let's start our first experiment, autocorrelation.
Known and defined sequence length. Maximum length sequences are simple to generate and 3 of such sequences are available at the sequence generator module. We will be mostly using a bipolar version of pseudo random bit sequence rather than being a 5 volt TTL level. It will be a plus or minus 2 volt data stream. This lends itself better for analog processing and is the same spectrally except for the lack of DC component. In this part of the experiment, we wish to compare a sequence with itself and with a delayed version of itself. This process is known as autocorrelation, meaning a correlation or comparison with itself. Another important point is that the comparison is carried out over the entire period of the signal, which is in this case is the entire period of the sequence. Figure sketched here is the operation of the implemented correlator for 2 cases. On the left is the condition where 2 inputs are aligned. On the right is the case where the 2 inputs are not aligned even though it is the same bit sequence. It is easy to see how the combination of multiplier, integrator and dump module are easily able to discern between the 2 conditions.
So these are the essential techniques for understanding the relationship within and between the signals. So let's dive in and see how it works in action. Let's see the initial setup to be done before starting our experiment.
Plug in the signals and system module in the expansion slot with the power off. Power up the ETT101C. Turn on the PC and wait for it to fully boot up. Launch the soft control panel and confirm USB OK message. Select the required tab on the soft control panel. Patch together the modules as shown to perform the experiment. In the software control panel, select manual entry to proceed further and look for DSP sampling frequency to be 2000, order 3 and select direct form 2 structure. To have point A at DAC output, select B0 as 1 and other coefficient of the B is 0. To have a point B at DAC output, select B1 is 1 and all the other coefficients of B are made 0. Confirm for yourself that the signal at point B and C are delayed version of the original signal from point A, using the oscilloscope to view both input and output to the DSP. The reference input is connected to the multiplier input XDC. The other delayed input to be compared is the input to the multiplier input Y. We will now compare the original sequence with itself. View the output of the multiplier and confirm that it is a constant DC level with downwards narrow spikes. Next is to view the integrator and dump output and confirm that it is ramping up until reaching the saturation as expected. The integrate hold output will hold the maximum voltage reached, which is the voltage at saturation. This will be the final constant DC value, which is easier to view. Now, to compare with the non-identical sequences, we delay the original sequence by several bit periods and repeat the correlation. Move the lead connected to YDC to terminal B. View the output of integrator and dump as well as input to the integrator and dump. Confirm that the output of integrator and dump is no longer ramping to saturation but is varying in both positive and negative direction. This is expected as the signal from the multiplier is no longer a DC voltage but is a varying bipolar signal.
The purpose of this exercise was to show you how these equations can be manifested as real. That's it for today's demo on autocorrelation experiment using Signals and System ETT101C add-on board and its experimenter kit. I hope this walkthrough has given you a clear understanding of how autocorrelation works and how it can be practically demonstrated. If you have any questions or thoughts, drop me in the comments below. I would like to hear it from you. Don't forget to like the video if you found it helpful and subscribe for more exciting experiments and insights. Thanks for watching and I will see you in the next video. Take care and happy experimenting.